Hey there, this is a video for my grade 10 MIAP students. I'm going to start with a little blast from the past for you here. Do you remember how your grade 9 teacher tried to convince you or prove to you that this rule must be true for all numbers except x, I should say cannot equal, x can't be 0. But for every other number in the universe, that is a true statement. Even fractions, decimals, even pi to the power of 0 is 1. Everything except for 0 to the power of 0 is 1. Why is that true? Well, if your grade 9 teacher just told it to you as a fact and never bothered to prove it to you, here's one really, well, there's two ways to do it. I'll show you. The main way is to just do it as what we'd call proof by exhaustion. You could say that, hey, how about something like 2 to the 3 divided by 2 to the 3? Well, that's actually 8 divided by 8, which is 1. But I also know there's something called the Quotient Law of Powers that says that 2 to the 3 divided by 2 to the 3 is also like saying 2 to the 3 minus 3. I can subtract the exponents because the base is the same, which is 2 to the power of 0. So if this thing is equal to 1 and this thing is equal to 2 to the 0, then by the distributive property of logic, those two things must equal each other. And then the proof by exhaustion part would go to the fact that, well, it really wouldn't matter what I picked for a base. This would always be true. So since I would exhaust every possibility in the universe except the possibility of the base being 0, I know that anything to the power of 0 must be 1. So that's one way to prove it. The other way that you can show as a proof is more of a pattern. And I always like this. Again, I'll stick with a base of 2 because it's easy to think about. 2 to the 5 is 32. 2 to the 4 is 16. 2 to the 3 is 8. 2 squared is 4. Okay, let's stop for a second. What's happening every time I go down 1 here? Well, I just subtract 1 from the exponent. What happens every time I go down 1 here? Well, you'd say I cut the number in half, or maybe better said, I divide by the base, which is 2. 32 divided by 2 is 16. 16 divided by 2 is 8. 8 divided by 2 is 4. So logically, 4 divided by 2 has to be 2. And now, what happens on the left in the next if I keep the pattern going? Well, 1 minus 1 is 0. And 2 divided by 2 is not 0, it's 1. So, once again, anything to the power of 0 has to be 1. So the reason I bring this up is, what if we kept going? What if I actually kept going? What's the next number in the pattern on the left? It'd be 2 to the negative 1. What's 1 divided by 2? Well, you guys love decimals, so you'd probably just say it's 0.5, but I prefer to think of it as the fraction 1/2. 1 divided by 2. What if I kept going? What's 2 to the negative 2? Well, again, it'd be cutting this number in half, which is 0.25, but again, I prefer the fraction. It's a quarter. What would be 2 to the negative 3? Well, it'd be a half of a quarter, which is 1/8. Now, do you notice anything? Notice the relationship between these two numbers here, for example? Because if you do, you're ready to fill it in here. We're on lesson 4.5 for roots and powers. And the rule is that x to the negative n is equal to 1 over x to the positive n. Negative exponents make reciprocals. So I'll use the example we just did. 2 to the negative 3 is like saying 1 over 2 cubed. Or, if you like better, 1/8.
Where is it?
So, let's do that. This is the rule.
I didn't see it when I put stuff in.
And here's my examples. 3 to the negative 2 would, of course, be 1 over 3 squared, which is 1 over 9. 7 to the negative 2 is 1 over 7 squared, which is 1 over 49. No, I do not want decimals. Now, this one, notice that that's in a bracket, so that negative is part of the base. So this would be 1 over negative 5 squared, which is 1/25. Please notice, if, I'm going to just make an extra one here, if this had been negative 5 to the negative 2, that would be negative 1/25. The negative here wouldn't get canceled by this exponent because it's only part of the base if I say that it's in a bracket like that. All right, now let's think about this one. How do I make this happen? Well, this is like saying 1 over 10 thirds cubed. Now, dividing something into 1, or really dividing by a fraction at all, first of all, 10 cubed is 1,000, and 3 cubed is 27. Do you remember that dividing by fractions, or dividing in fractions, is like multiplying by the reciprocal? So that's like saying 1 times the reciprocal. So that's going to be, and of course timesing by 1 is pointless. It's just going to be that. Now, there's a nice little shortcut to this. I'm actually going to even put it maybe as a rule up here. I'm going to say that 1 over x to the negative n is just x to the positive n. Or, similarly, a over b to the negative 1 is just b over a. Because negative exponents make reciprocals. So, by this logic, I can kind of do this one with less work than that. If that rule there that we just talked about makes sense to you, I can say that basically all I have to do is cube these two numbers. And of course, when you cube a negative, you get a negative, right? A negative times a negative times a negative is still negative. So this is going to be a negative, but it's going to be the cube of 4 on top and the cube of 3 on the bottom. See if you can understand why that works. And down here, this is like saying 1 over 1 over 3 to the 4, which is going to, when you divide by the reciprocal, just move the 3 to the 4 up to the top. So I didn't even really need that. I could have figured out from the rule that that would become that. Cool. All right, so that's kind of the first part of the lesson here. Let's do some more examples. Suppose I had 8 to the negative 1/3. Ooh, do you remember from the last lesson what it means to be a power of a third? That's going to be 1 over the cube root of 8. And it says evaluate, so that is 1/2. This is going to be the reciprocal of this square rooted. So it's going to be equal to the square root of 36 over 25. Right? The negative part reciprocals it, the 1/2 square roots it. Would it help if you thought of this as 25 over 36 to the negative 1 to the 1/2, and then you times those two exponents together? But that means that this is, of course, reciprocaled first. Oops. Reciprocaled first, and then square rooted. Again, I wouldn't need to write this down if I understand how the rules work. I would go right to here and find that this is, of course, 6 over 5. All right. If that's making sense to you, why don't you try this one? 16 to the negative 3/2. So first things first, it's going to be a reciprocal. And then it's really 16 to the 3/2. Do you want to go 16 cubed square rooted, or do you want to go 16 square rooted cubed? I think I'd rather do the square root first because I know what the square root of 16 is. I have no idea what 16 cubed is. So it's going to be 1 over 4 cubed. And if you need a step between there and there, I would write it like this, if you like. And then that would, of course, be 1 over 64. Okay. Oops, sorry, I'm off the screen. All right, now this one. The negative makes it reciprocal. There, I used the negative. It's not there anymore. Now, you know what? This is supposed to be a 4. That's a typo. You want to fix that? 63 is not a perfect square or a perfect cube. There we go. Now I'd like the cube root of this thing, which is going to be 5 over 4. And then I take it to the power of 4. So first I used the negative, then I used the third, now I'm using the 4. And 5 to the power of 4 is 5 times 5 times 5 times 5, which is 25 times 25, which is 625. And 4 times 4 times 4 times 4 is 16 times 16, which is 256. By the way, calculators are capable of doing these things, and they're capable of doing them in fractions. If I were to enter this in my calculator, I could go open a bracket, 64 fraction 125, close brackets, to the power of, and then open a bracket again and go negative 4 over 3. And then close the bracket for the exponent and hit equals, and I actually don't even know if this is going to work. It should. And oh, it changed it to a mixed number. Just go second function fraction button and see that'll actually make it an improper fraction. And yeah, there it is, 625 over 256. Question like that, I probably wouldn't let you use a calculator on the test, but there you go. Calculators can do it. Oops, just knocked my microphone over. Okay, so that's actually all there is to the 4.5 lesson. After that, there is kind of a quick little. I'm just going to maybe work through it right now because this was fairly short. There is a kind of a quick refresher on all of your exponent laws, and of course it starts with the ones that you learned in grade 9, right? The product of a power rule is basically what we'd usually just call product rule, which says that if I have that base to this power and then that base to that power, it's really just add the exponents together, right? Like say, for example, 2 to the 3 times 2 to the 4, that'd be 2 to the 7. So there's the first one. The second one's the quotient rule, which says that if I have a division where the bases are the same, I subtract the exponents. Keep in mind this is only true when the bases are the same. So if I had, say, 2 to the 6 divided by 2 to the 3, that's a 3. 2 to the 3, sorry, this is why I don't write in pen very much. That would be 2 to the 6 minus 3, which is 3. Okay, and you can check that with numbers if you want. That's 64 divided by 8, which is 8. Okay, so there's the second one. And then, of course, there's power of a power, which says that if you take a power to another power, you multiply the exponents. So say I had 2 to the 3 to the 4, that would actually be 2 to the 12, which makes sense. That'd be 8 times itself 4 times. 8 times 8 times 8 times 8 is, I think that's 4096. You could punch that on a calculator if you weren't sure. And then there's power of a product rule that says that if you have a product times a power, that's the same as both of those bases to that power. You can distribute an exponent into a product. You can also distribute an exponent into a quotient. Make sure you understand that it is completely illegal to distribute a power into a sum. That is not, that is not true, right? We talked about this. I can show you for a fact it's not true. Suppose I had 3 plus 4 squared. Is that the same as 3 squared plus 4 squared? Heck no. That's 7 squared is 49. That's 9 plus 16 is 25. Those are not at all the same. You can distribute exponents into products and into quotients, but not into sums or differences. Okay? Then there's the one we were just talking about earlier. X to the power of 0 is equal to 1 as long as x is not equal to 0. Actually, to be honest, this one probably should say that too. This, of course, is only true if y is not equal to 0, because you can't divide by 0. And this one also, you'd have to say that if x is, of course, not equal to 0, otherwise you'd be dividing by 0. So if I'm going to say it for this one, I should probably say it for those. And these were the power rules that you had back in grade 9. Then, I don't know how algebraic your grade 9 class got. When I was teaching at Acadia, and I was there for 18 years, certainly with my honors group, I had to do this stuff because I was going to teach them grade 10 as well. But if I had a stronger grade 9 class, I would make them do stuff like this. The grade 9 curriculum says that you have to learn the power laws just with numbers. You don't actually have to do them algebraically with x's. You don't even have to show them the laws in x's and a's and b's if you don't want to, because the grade 9 curriculum says you only have to understand with numbers, not with symbols that represent numbers, in other words, algebra. But if I had a stronger class, and I know that most of these guys are going to take MIAP in grade 10, I would do these kinds of questions. So this, tell you what, why don't you pause the video, and for examples 1, 2, 3, 4, 5, 6, and then we wrote 5 and 6 again because we apparently can't count to 8. So for these 8 examples, pause the video and give them a try yourself. See if you can do those 8 examples, and then I'll run through them for you in a minute. Okay? On your mark, get set, pause. All right, did you try them? This one would be x to the 10. This one would be x squared y to the 4, because I subtract. Remember, x means x to the 1, right? So I subtracted exponents there. And no, I can't say that that's xy to the 6. That doesn't work, right? Those are two different bases. This is x times y times y times y times y. Can't simplify it any more than that. Okay, so make sure you got that one. All right, how did the next page go? Did you get 30 x to the 5 y to the 9? Here, did you get 9a to the 8b to the 4? Right? I'm still squaring 3, but these exponents get times by 2, not squared. Make sure that makes sense to you. Here, did you get x to the 6, y to the 9 over 64w cubed? And here, make sure you understand that this 2 is not being taken to the power of 4. Bedmath says do exponents, then multiply. So this is 2x to the 24. It is not 16x to the 24. Make sure that makes sense to you. And then example 5. All right, for this one, I'm going to square everything in the bracket first, and then cube everything in this bracket. Then I'm going to add those exponents together. Did you get 9x to the 14? And for this guy, ooh, this one's fun. I like bedmath. I like trying to simplify what's in the bracket first, then I'll worry about what's outside. So I'm going to simplify 10 and 15 simplifies to, they both divide by 5, so that's 2 over 3. And then x to the 8 divided by x to the 4 is x to the 4. And then y to the 6 divided by y is actually y to the 5. And then I'm still squaring everything. So that's going to be 4x to the 8, y to the 10 over 9. All right. That's about as tough as anything a grade 9 teacher might have thrown at you. And again, some of you might not have even seen anything quite that complicated algebraically in grade 9. That'll set us up for our last lesson on new things in this chapter 4. And we'll do that next time. Okay? So check the blog for the homework on 4.5, and we'll see you next lesson.